Okay, so I'm recording this lecture on 3.7, which is optimization, in 2014. I guess I didn't have it up on my website, so thought I'd do it since someone asked me for it, and this time I guess it wasn't Sana and Sabika. So it was someone else. Arjun, actually Sagar, asked me to do this. And this is really an important topic, and I think it's probably worthwhile getting this recorded because calculus is one place where, well, actually optimization is one topic which is a true application of calculus, okay? And optimization can mean many different things for different people. For the capitalist, it's going to be maximizing profits or minimizing losses. For an aerospace engineer, it might be minimizing the amount of fuel to take a satellite or a rocket up from one orbit or a satellite up from one orbit to another, and so on. So it means different things for different people. But the techniques are very similar. So I'm going to start out with a problem that can really be done by Algebra 2. Okay? Can really be done by Algebra 2. But we'll do it by calculus, and then we'll kind of use Algebra 2 or really Algebra 0 to make sure that that we are doing things correctly. So this is a problem, okay? You're given a wire fencing material that is 24 feet long, and you want to make a rectangle out of it, and you want to find the dimensions of the rectangle so that the area is a maximum. So if I were to make my rectangle L by W, then given that this is the perimeter, you know that 2L plus 2W has got to be 24, okay? Which means that L has got to be equal to 12 minus W. And the area is going to be width times length, okay? And hence you get this, okay? Hence you get that. So that's the area. This is called the objective function. This is called the objective function. Okay? And this equation here that you start out with is called the constraint function. So the idea is that you want to maximize dA by, you want to maximize A, which is a function of W. So if you were to graph this function, okay, with A on the y-axis and W on the x-axis, you know that when W is equal to 12, you're going to go to a 0. When W is 0, it's going to be 0. You know this is a parabola that's opening down. Okay? And from Algebra 0, we know that the maximum happens at the vertex. And the x-coordinate of the vertex from Algebra 0, I'll call this xv, is equal to minus b over 2a. So if I were to rewrite this as a traditional quadratic equation, I get minus w squared plus w, 12w rather, and you can see that b is equal to 12, a is equal to -1, so then this would become 2, and the x-coordinate is 6, okay? So you know that it's going to be 6 for the width, okay, because this is the axis on the x-axis is the width, so that'll be your width. In this case, it's feet, okay? And if you were to take this and you plug it in here, then you know that the length is also equal to 6, okay? So a rectangle at 6 by 6 would be the maximum area, which turns out to be a square, okay? Well, that's Algebra 0. What we want to do is we want to do some calculus on this, okay? And the reason why this topic is in chapter 3 is because we started out with 3 in terms of finding the extrema of a function. So remember, an extrema is either a minimum or a maximum. In the context of the current problem, we want to find A to be the maximum. So if I differentiate, let me get another pen out here. I'll do black. If I differentiate my function, I get dA by dW is equal to minus 2W plus W plus 12 equals 0, which gives me that W is equal to 6. Okay? Remember, W is the width of the rectangle. And then you can get the length by the same method that we did earlier by plugging into this equation here. Now we need to take it another step further and make sure that we show that this is indeed a maximum. So if I look at the second derivative, d2a by dw squared is equal to negative 2, which is less than 0. Therefore, this is a Canadian, which implies it gives me a max. Okay, so this step is really necessary. So you can either use the second derivative test or the first derivative test. Okay, I use the second derivative test in this example. Okay, I have one more example to do. And then all the other examples really follow the same style. Okay, so that's the question. Okay, which points on the graph y equals 4 minus x squared are closest to the point 0, 2? So here's my point 0, 2. And here's my arbitrary point on the graph, x, y. So since it's asking for the closest, we obviously need to find the distance. Okay? So going in to find the distance and using the distance formula, the distance between x, y and 0, 2 is going to be x squared plus y minus 2 quantity squared. Okay? And we want to make this a minimum because it's getting it to be the closest. Now with the square root sign, things get really ugly, okay, in terms of the derivative and so on. So why don't I just instead do the square of it? Okay? So in other words, if I minimize this guy, okay, I'm guaranteed that this is also going to be a minimum. Okay? Right? So this is my objective function, okay? That's my objective function. And this here is my constraint. So if you look at the objective function, it's got two variables, and really we want only one variable, so we can do a differentiation. Okay. So what I can do is I can take this value, okay, and shove it in here, and so I get d is equal to x squared plus 4 minus x squared minus 2 quantity squared, which is equal to x squared plus 2 minus x squared quantity squared. Okay. Now I could go ahead and FOIL this and do everything like that, but I'll just leave it like that and use the power rule and the chain rule. Okay. So if I do a differentiation, I get dd by dx is equal to 2x plus 2 times 2 minus x squared times the derivative of the inside, which is negative 2x. Okay. So this gives me 2x. The 2 there and that 2 and with a negative sign becomes minus x minus 2x. Sorry, it becomes minus 4x times 2 minus x squared. And this gives me 2x minus 8x plus 4x cubed, which is equal to 4x cubed minus 6x equals 0. And so if I factor 2x out of there, I get 2x minus 3 equals 0. And I get x equals either 0 or 3 over 2. Okay. So notice there are two possibilities. It could be either 0 or 3 over 2. So maybe one's going to give me a max and the other one's going to give me a min. I don't know. So why don't I do the second derivative of this, okay? So I do the second derivative and I get d2 d squared by dx squared is equal to negative 6 plus 4x. If I put x equals 0, then obviously what I get is negative 6, which is less than 0. This would give me a Canadian and therefore would make it max. So 0 doesn't work. Okay? And if I put in 3 over 2 in here, okay, if I put 3 over 2 in here, which is my second derivative, okay, I get minus 6 plus 4 times 3 over, actually, yeah, oh, do I want to do that? No, I don't want to put 3 over 2, my bad. Yeah, I do want to put 3 over 2. So then what would happen here? I did F up here, didn't I? This ought to be 12x squared. So let me go fix that, okay? Let's just redo this. So you guys can see I do make a mistake, but the important point is to fix your mistakes, okay, if you recognize them. All right, so I'm going to go in here, and so this is going to be minus 6 plus 12x squared. And x equals 0 doesn't work, okay, just like I told you earlier. However, if I put x equals 3 over 2, then this becomes equal to negative 6 plus 12 times 9 over 4, which is positive, gives me a cup, which gives me a minimum. So I know my x value is going to be 3 over 2. To get my y value, I take 3 over 2 and shove it in here, okay, in here. That'll give me my y value. So y would be equal to 4 minus 9 over 4, which is 16 would be 7 over 4. So the answer should be 3 over 2, comma 7 over 4 is the point closest to the point 0, comma 2. Let me just make sure that I haven't screwed this up. I do get x equals 3 over 2. If I shove it in there, it becomes 9 over 4. 16 minus 9 is 7. So your answer is 3 over 2, 7 over 4. Okay? So most of the problems are done in a similar fashion. You write down the objective function. You write down the constraint function. You take one of the variables out of the constraint function and you put it in the objective function. Differentiate, get a critical point, show that the critical point achieves the objective you are trying to reach, either by the first derivative test or the second derivative test. Okay?